In this lecture, we'll discuss some of the history of GPU computing, explain how modern accelerators diverge from graphics processing in some key ways, and finally consider what opportunities GPUs present for high performance in scientific computing. Graphics processing units, or GPUs, are specialized processors designed to accelerate the processing of graphics and other visual content. They are widely used in various applications, including gaming, scientific simulations, and machine learning. Indeed, GPUs have seamlessly integrated into modern computing systems, offering significant performance improvements over traditional CPUs for some specialized tasks. The term GPU might be a misnomer, as every GPU in 2025 is effectively a general-purpose processor adapted to highly parallel numerical tasks rather than only graphics. That is, these are general-purpose graphics processing units, or GPGPUs. These devices are treated as accelerators focused on the execution of embarrassingly parallel tasks, limited by floating-point operation throughput, and as such often form the backbone of many high-performance computing systems. Throughout this lecture, we will make a distinction between the CPU and the associated main memory, and the GPU and its graphics memory. We refer to the CPU and its memory subsystem as the host, and the GPU with its memory as the device. Some modern chips incorporate both processing units with shared memory. We ignore this complication for now. The history of GPU computing stretches back to the 1970s with specialized graphics circuits in arcade games, followed by the introduction of the first dedicated GPU chip, the NEC 7220, in 1981. The 1990s saw the dissemination of OpenGL, enabling more accessible GPU programming. In the 2000s, researchers and developers began creatively using the graphics pipeline for matrix computations, a trend that paved the way for more general-purpose applications. A significant milestone was NVIDIA's introduction of the G80 in 2008. This was the first truly general-purpose GPU, accompanied by the CUDA programming model. The 2010s witnessed the development and advancement of low-level unified graphics compute architectures. Today, GPU computing is commonplace in AI and HPC applications, and the future points towards ubiquitous heterogeneous compute environments like our current CPU and GPU systems, spanning from consumer devices to high-performance computing systems. GPUs, having derived from the context of graphics processing, organize thousands of threads to perform highly parallel numerical tasks. These calculations benefit from being highly uniform in the sense that different portions of the hardware see identical instruction sequences with different input data. This design maps onto the application of image processing tasks or the updating of pixels on a screen. Based on our understanding of Flynn's taxonomy, we might suspect the GPU represents either SIMD or MIMD hardware. GPUs famously coordinate thousands to millions of threads and rely on similar instructions occurring for high throughput. In fact, GPGPUs are both SIMD and MIMD, though arguably at different levels of abstraction, and they use both to effect extremely high-throughput floating-point calculations. The architecture is sometimes referred to as SIMT, single instruction, multiple thread, even though this description is not entirely accurate for modern, compute-oriented GPGPUs. Modern GPUs are largely organized in similar ways, though the nomenclature varies between vendors. Importantly, the notion of a core on a GPU is very distinct from the CPU context, and indeed between different GPU vendors. The nomenclature for GPUs is also corrupted by marketing. For instance, NVIDIA refers to CUDA cores, while AMD uses stream processors, and Intel uses execution units. These are marketing terms to describe a familiar, if largely useless, quantity: the number of single precision floating point operations per cycle. Generally, a GPU is composed of a hierarchy of hardware building blocks. At the lowest level are the scalar processing elements, or ALUs, grouped into functional units such as streaming multiprocessors, or SMs, on NVIDIA GPUs, or compute units, CUs, on AMD GPUs. Each SM on an NVIDIA GPU schedules threads onto a block of ALUs, which share an L1 instruction cache and operate in a SIMD-like fashion. The memory hierarchy of GPUs is a frequent source of confusion. At the largest level, GPU global memory is the largest memory block available and is accessible to all the threads on the device. The global memory has, typically, high latencies and high bandwidth. It is both physically far from the compute units and the largest pool of accessible memory. This makes it ideal for storing the main part of your data, but optimizations for repeated access should be considered carefully. Global memory is the memory which must be copied to at the beginning of a GPU calculation and copied from at the end. Additionally, each SM has access to a segment of shared memory. This level of memory enables some shared memory parallelism alongside local synchronization of the threads in the block. Shared memory is low latency and high bandwidth, but limited in size. This is mostly useful for accessing data many times in a calculation, like the tile of a matrix inside a GEMM. Importantly, it is often the case that the hardware used for the L1 cache for each SM is shared with that used for shared memory. Thus, at this level, careful testing is needed to determine the impact of explicit use of the shared memory alongside the automatic use of L1 caching. Finally, each thread has its own private memory, which acts as registers and temporary storage for intermediate results. As usual, calculations which can be kept in register benefit from extremely low latency access. However, the register pressure of 16 or 32 threads reading and writing intermediate results means this may also become a performance limiter for some calculations. Recent changes in how GPU accelerators are designed and built have led to changes in the conception of the memory hierarchy. In the consumer space, combined CPU and GPU designs have been de rigueur since 2011. In the HPC space, both NVIDIA and AMD are pushing combined hardware designs, where CPU and GPU share main memory so that copies to and from the GPU segment are no-ops, which can dramatically change the calculus for whether a GPU calculation is worth it. The development of largely synchronous GPU programming models has left us spoiled for descriptions of the arrangement of threads, blocks, grids, warps, and the like. In CUDA, for example, threads are organized into blocks, and blocks are further organized into grids. Each block has its own shared memory, and each thread has its own private memory. In OpenCL, threads are organized into work items, and work items are organized into work groups. Each work group has its own local memory, and each work item has its own private memory. This is all to say that GPU programming models do not typically expose single-thread calculations to the programmer in the same way that CPU programming models do. Instead, GPUs engage in a dual-level approach, where the lower level within an SM corresponds to a SIMD-like vectorization model, while the upper level across multiple SMs corresponds to an MIMD-like threading model. In practice, programming a GPU happens from the CPU. We initialize and prepare one or more queues attached to the device. We copy data from the main memory to the GPU memory, or pass the pointer over in a shared memory context, and then issue directives in the form of kernel functions which execute on the GPU hardware. In practice, the kernels are something analogous to the loop iterator code, the interior of whatever outer loop one would normally write to compute with the input arrays. The kernel executes across multiple data elements simultaneously by managing the indexation into the data through the thread and block indices. For example, by computing a global offset into the array for the selection of some thread-specific value. Now, GPUs are designed to achieve high throughput by scheduling thousands of threads to perform millions of calculations simultaneously. However, this parallelism comes at the cost of increased latency due to the need for high bandwidth memory access and hardware synchronization. It thus becomes essential to hide the latency of the calculations from the programmer, and to this end, GPUs employ various techniques such as pipelining, caching, and instruction-level parallelism. Finally, GPUs exhibit the same arithmetic intensity difficulties as CPUs. On a GPU, the performance of the program is largely determined by a quantity called the occupancy. This is a measurement of the usage of the available hardware resources. This quantity can vary over time and across different elements in the GPU, and its calculation is beyond the scope of this lecture. However, considerations for GPU performance should begin with the occupancy. An alternative approach to improving the arithmetic intensity is to do more computations per byte. The machine learning community has largely spearheaded this use of mixed or low precision data types to enhance the arithmetic intensity on modern GPUs. And this exciting development continues to make inroads in scientific computing as well. In summary, GPUs have earned their ubiquity in HPC through realizing the goal of a multi-level hierarchy of parallelism, and for better or worse, these devices now inform the design of scientific software the world over. We've discussed some high-level aspects of the hardware and software of GPUs, and some of the more important elements of analyzing the performance of calculations on them.